Thank you for being here. I watched many videos of HAO, so it's quite a particular feeling to be here today. It's a big pleasure. So starting from the title of the presentation, mostly as it was introduced before, and also as it is suggested by the title itself, I work on the Thermosphere products, mainly on natural density and wind from satellite acceleration observations. Mainly I work on 4 missions, so starting in chronological order. I work with CHAMP data. CHAMP was a German satellite and provided for more than 10 years information about the Earth's magnetic field and the gravity field. Second mission that I work with is GRACE, that is using 2 twin satellites in order also to look at the gravity field of the Earth. And it was launched in 2002, and it was operative until 2017, so 15 years of very nice data. The third mission is the European Space Agency GOCE. GOCE indeed was an excellent mission that provided very interesting information about gravity field anomalies thanks to its gradiometer and also thanks to its very, very low altitude with respect to the satellites that we are used to work with in LEO orbits. And last but not least, the European Space Agency's SWIRM mission, that between all the satellites that I cited before is the only one that is still alive, is over our heads, and is flying with 3 satellites, SWIRM Alpha, SWIRM Bravo, and SWIRM Charlie, that are also known as SWIRM Alpha A, B, and C. Mainly, they are flying in polar orbits. SWIRM A and C are flying pretty close to each other at around a few kilometers over, let's say, 400 kilometers of altitude, and the SWIRM B is mostly flying at 100 kilometers, more or less, over them. So these missions are providing very interesting data. If we will take a snapshot of the last 20 years of data, let's say, and we look at this plot, for example, in which we see the altitude evolution in function of time, we can see in green CHAMP, in blue GRACE, in orange GOCE, and on the top right the SWIRM family. So we can see in the background that there is in gray color the F-10-7, the mean F-10-7, 81 days mean. So we can see clearly that these 4 missions are providing us crucial information about the thermosphere in terms of solar activity, but also in terms of altitude, because we are ranging between 250 more or less from GOCE, almost reaching 550 with SWIRM. But life is not easy, because if we work with so many satellites, we also have some problems. This is just an animation that I created at the beginning of my PhD. It doesn't show in-flight data, but it's providing an idea of the problem that we are facing. So basically here we have GRACE, and if we plot the density difference with respect, for example, an atmospheric model, and we compare it with other 2 satellites, for example, GOCE on the top and SWIRM below, we see that the data sets that we get are with a bias between the atmospheric model, but also between different missions themselves. So what I want to do within my research is to look into these bias differences, and most of the scientists right now are neglecting these biases, or they are using like ad hoc scale factors in order to tune these data sets. But it's crucial to remove them because of 4 reasons, let's say. Mostly because if you are looking at 2 satellites that are flying at the same time, let's say, and you want to combine the data from these 2 missions, mostly, indeed, you have to compare similar things without a bias difference between themselves. Also, if you look at long trend changes, if you combine more missions also in time. Also there you require minimal bias differences. And also if you study different systems like the coupling between, for example, Thermosphere and Ionosphere. And from a practical point of view, it's also really important to have an accurate information about the satellite drag modeling, because this is necessary to understand, obviously, for the new mission that we are designing right now, how long they're going to stay at a certain altitude, or it's also important for planning maneuvers, so how much fuel we need and when we need to do this maneuver. So at the beginning of my PhD, indeed, what I did is to start from zero. These errors, these biases are mostly related to geometry and aerodynamic modeling problems. So if you don't accurately describe the satellite outer surface, you're going to have troubles. And what I did is to start from zero, indeed, and to design thanks to a CAD software, the new geometries of champ, grace, gauge, and swarm, and to run some direct simulation Monte Carlo in order to estimate the forces that were acting on them. So what was done in the past was mainly based on the approach of the panel method. The panel method is a method that is based on analytical solution applied to a limited number of flat panels. But as you can see in this slide on the top, I just cropped the first panel of the swarm macro model. We don't have many information. We have just information about area, about the normal vector, and a few additional informations about material and emissivity and reflectivity that are important, for example, if we want to model the solar radiation pressure. But we don't have information about where these panels are, so it's impossible to deal with multiple reflections and also shadowing, because we don't know where these panels are exactly. So what I indeed propose is to use a direct simulation Monte Carlo approach using a gas dynamic, rarefied gas dynamic solver called Sparta, and put as input my new high fidelity geometries. So now we are describing the satellite geometries with all the possible details that we can retrieve from the technical drawings, for example. And now, running these simulations, we have finally information about shadowing and multiple reflections. Obviously, this doesn't come for free, because indeed it's quite a complex approach and also expensive from the computational point of view. So just to give you an idea of the differences that we can get from the aerodynamic point of view, if we compare the two methods, in this slide we see the results for CHAMP. On the left, on the vertical axis, we have the aerodynamic coefficient. On the horizontal axis, we have the attack angle, that in this case is varying between -6 and 6. And with solid lines, we have the results for the panels method with the markers DSMC method, and with blue drag coefficient, red the lift, and in green lift over drag ratio. On the right, we have just a zoom in of what we see on the left below. So what we can see is that there are some differences. Also, if we look at different analysis that is varying the side slip angle, these are not particularly relevant for CHAMP, I would say, but for example, if we change the satellite, like for SWARM, we can see that these differences are getting quite large. Here is for the attack angle variation, but here is also for the side slip angle variation, and we can reach for like the nominal flight configuration differences that reach up to 32% between the two methods. If we translate this information in natural densities, basically here in this slide we see the results for SWARM C. I think, if I remember correctly, like for 3 years of data between 2014 and 2017. On the vertical axis of these plots, we get the NRLMSIS density, and on the horizontal one, on the left, what we had in the past, the panel density, and on the right, the new one, Sparta. Basically, the cloud size and shape doesn't change, but mostly what we get is that we get closer to the diagonal. That means that we get a better agreement with the semi-empirical model. In order to understand if we are also on the good way, if we have a very good geometry model of the satellite or not, what we can do is to use an attitude maneuver. Because if we look at an attitude maneuver in a very short time, let's say the atmosphere is not changing that much, the density is not changing that much, but if you have not an accurate description of your geometry modeling, you might see that there is a jump in your data, and we don't want that. So if we do things correctly, we should expect like a stable behavior of the density. So this is a maneuver that occurred in 2014, in May 2014, nearly at the beginning of the mission, high solar activity. In the top two plots, we see the X and Y accelerations. We can see indeed that after midnight, they are kind of switching with each other, and there is where it's starting the maneuver. And in the last three plots, we see the densities from Sparta that are in blue, the densities from panels method that are in yellow, and the dashed lines are for respectively NRLMSIS, JB 2008, and DTM 2013 that are semi-empirical models. So from here you cannot see so much, so I will try to zoom in, for example, in the results in the comparison with DTM 2013. So mostly what we can see is that before the maneuver, when the satellite is flying pretty much in a nominal configuration, there is a big difference between the yellow line and the light blue lines. But after, and the panel's density is totally underestimating the density with respect to the Sparta model. But if we go inside the maneuver, in the other gray shaded area, we can see that it's even jumping over the Sparta densities, whereas these densities for Sparta, they are pretty stable. So if we look just at the two gray areas and we overlap these two periods, we can see what are mainly the differences between inside and outside the maneuver. And we see that the model is a little bit overestimating probably the densities. Sparta is pretty much having a very consistent results between the two orbits. But if we see the panels densities, we can see that there is a big jump between the two different orbits, and that we reach even more than 50% of difference between the two density subsets. So this is something that is now fixed and is also implemented in the new density processing. Obviously, I did the same for the additional mission, Champ, Grace, Goce, Swarm, B, and C, that is equal to A mostly. And what we can see here is that basically we consistently go closer to the atmospheric models, even if we change missions or change atmospheric models. The atmospheric models are performing in a different way between each other because they are sampling different data. They are described in different ways. But indeed, what we see is that the yellow blocks are getting closer to 1. That is the mean ratio between the newly derived densities and the semi-empirical model densities. And if you are interested in additional details, I suggest you to look into this publication that we published in Advancing in Space Research Journal.
Can I have a question?
Sure.
So does Sparta treat the interaction between the atmospheric molecules themselves and the spacecraft in the same way in the panels and the Sparta calculation, or do they treat that in? I know the shape and everything else is different to the angles, but is the actual, whether it's sticks or whether specular and all
Most
that
probably I will arrive to this point later.
Okay.
You are meaning mostly the gas surface interactions?
Yes.
Yeah.
Yes.
So
you're getting to that.
Okay. Yeah. It's my second part. I will go into that. So, yeah. In addition to this part, what we are doing also in Delft, together with my colleagues, is to work for ESA to provide the level 2 density. Basically, let's say that swarm mission is a pretty cool mission. But from the accelerometer point of view, we got some big issues. Here in this plot that is quite famous within the swarm community, we can see like the 2 years of swarm C data, densities, not densities, but the steps, the corrected steps, because this accelerometer output were providing big gaps, and they have been corrected, but indeed the quality of the accelerometer data were not so satisfactory. So it was necessary to create a new product, a new acceleration based not on the accelerometer data, but based on GPS measurements. We did that, and nowadays, indeed, you can have swarm densities since the beginning of the mission, until now. In this plot, in this slide, we see mostly on the top swarm A density and below swarm B densities as a function of time and argument of latitude on the vertical axis. Take care about the color bar, because indeed swarm B is flying at more or less 100 kilometers over. So indeed the color bar is like half of what is for swarm A. So densities are much lower. And in the bottom part of this slide, we can see also the geomagnetic and solar activity information. And as we can see, we have kind of a steep decrease of the geomagnetic activity and solar activity. And indeed, we can clearly see it also in the data that are getting lower and lower in magnitude. But we can still have a lot of fun also looking at big events like it happened in March 2015. And this animation was showed, I think, by Jelko Dornbros in a couple of years ago in a EGU conference, and it's showing indeed the storm that happened in March 2015, the so-called St. Patrick storm. On the left, we can see mainly as a color plot over the globe TI-GCM densities, and also close to the auroral oval, the data from AMI. And we can see also the magnetic field information along the orbits of swarm B, swarm C, and swarm A. Yeah, now we start to see that indeed something is going on. And on the right, we see the densities from swarm C compared to TI-GCM model. So this is quite a nice animation, but it's also crucial if you work with models, because it's really important to assimilate this information and this data in order to improve what we currently have. And here we are. Indeed, in the second part of my PhD, the first one was mainly based on the geometry and the outer surface modeling of the satellite, also aerodynamics with the gas, with the DSMC approach. But still, we can keep working on the aerodynamics under the gas surface interaction investigation. With gas surface interactions, I mainly mean the interactions that we have between atmospheric particles and the satellite surfaces. If we speak in black and white, let's say these reflections can be divided in two modes: specular reflections and diffuse reflections, and the drag coefficients are function of these different modes. Mainly what we have from the few observations in space at satellite orbits, we see that mostly what is suggested is that we have diffusive reflections. So in this study, what we did is mostly to neglect the specular contribution. And the diffusive reflections are mainly driven by the energy accommodation coefficient, that is this parameter alpha E that you see below. It is a function of the satellite surface nature and state, and also of the gases that are accumulating nearby the satellite surfaces. It's also a function, mathematically speaking, of the incoming temperature of the particle, so before the collision, the emitted temperature, so the temperature that this particle have after the collision, and also function of T-wall that we see at the denominator, that is the surface temperature of the satellite. This value is ranging between 0 and 1. 0, we have it if the emitted temperature is equal to the incoming temperature, so for specular reflections, and 1 when the emitted temperature is fully adjusted to the wall temperature, so TRE is equal to T-wall. What is currently used in the thermospheric products processing is a value of 0.93. And mostly in my research, what I'm finding out is that most probably this value might be a little bit smaller, so lower than 0.93, and I will show you a little bit later. So the first step again is to start again from the aerodynamics. That is fundamental for these kind of products. So basically, here we have the results for grace. In the 3 polar plots, we have the aerodynamic information of Cx, Cy, Cz, that are the aerodynamic coefficients along the spacecraft reference frame. And it's important to have a complete data set for each accommodation coefficient. So here we can see that for accommodation coefficient equal to 0 with the red lines, so we have the maximum of the aerodynamic coefficient magnitude, and we get lower if the accommodation coefficient is going up. So in order to understand, for example, this left plot here in the polar plot, we are changing the yaw angle. So we start from the nominal flight configuration around 0, we go up, and around indeed 30 degrees, we reach the maximum of the area that is seen by the flow. And after we go to 90 degrees, and the x contribution of the aerodynamic coefficient is 0. And this is continuing because mostly for Grace is a pretty symmetrical satellite. So if you turn it of 180 degrees, you mostly have the same results. This doesn't happen for CHAMP. CHAMP was characterized by a frontal boom. And you can see indeed that there is a difference if you look at the CX information between the right lobe and the left lobe. And it's also funny to see that if we change satellite with respect like to CHAMP, and we look at SWARM that has mostly kind of similar shape, but flipped of 180, you get this asymmetric shape that is indeed flipped. So indeed, you can see it in the data. And also the influence of the energy accommodation coefficient look like is changing depending on if you have the frontal boom. There you see that the lines are a little bit close to each other, so there is less influence, and here is a little bit larger if you have a flat surface at the beginning, like this one in the picture here below. So to translate this information, the aerodynamics, into densities, in this plot we can see the density for Gauche on the top. Again, we have the information about the geomagnetic activity with AP, and with the gray color, the F107. We can see that for Gauche, the solar activity was rising up, and also the density is rising up. And below, indeed, we see the density as a function of time in 3 years of data of Gauche. In red, we see the densities for NRLMSIS, 0, again. In blue, those ones for Sparta, and in yellow, those ones for the panels. And if we decrease, for example, here is for 1 of accommodation coefficient, and if we decrease to 0.93, we see that the densities are getting lower, and this also continue to happen if we decrease and decrease the energy accommodation coefficient. Obviously, this doesn't happen only for Gauche, but if you change the satellite to SWARM A as well, here we have a descending slope of the solar activity, but we get also the same decrease of the density. So we are getting farther from the models, but this is not entirely bad news, because anyway, we know that the models are not perfect, are not the truth. So what we want to do is to look more at the satellite data itself in order to find an optimal value of the energy accommodation coefficient. And what I found out is that it's easier to work on gas surface interactions if you are looking at the winds. This is an analysis that I did always about an attitude maneuver. I really love attitude maneuvers in my research. And this is for a CHEM satellite. This maneuver occurred in November 2002. And here we see again a similar plot to what you have seen before. On the top we have the x accelerations and below the y accelerations. And we clearly see that indeed around the midday here the satellite is moving in a normal position with respect to the flow. And if we highlight 3 different periods, in green before, red during the maneuver, and blue after the maneuver, and you try to catch, let's say, as much as possible the same thermospheric conditions. So we look, for example, indeed here we are slightly after noon. So we look at the 24 hours before and after. We try to minimize the thermosphere variability, and we kind of see the same magnetic field characteristics. So we try to minimize the possible variabilities. And if you look at the zonal wind, in this plot is zonal wind as a function of the argument of latitude for those 3 orbits that we see. So here the colors are again correlated to the colors that you have seen before. So green before, red in the middle, and blue after. And together with them there is also the HWM14 model with the open circle. We can see that for energy accommodation coefficient equal to 1, we get this difference between the winds, the zonal winds, but if we decrease it, we get that these winds are kind of getting closer to each other. If we keep decreasing, we get maybe indeed an optimal from what it looks like from here. But if we keep decreasing, we get again big differences. So I can play around with it, and indeed it looks like for 0.85 we kind of have an optimal. And what I did is to look, obviously I try to minimize all the possible error sources that we can have, and one strong error source, the source that we have, is the solar radiation pressure. So what I did is to look at the eclipse period in which we have no sunlight. In this way, these data were a little bit cleaner. And what I also did is to don't look only at one orbit at the same period, let's say, but I took all the possible orbits that I could take within the maneuver. Was maximum allowed of 6 orbits. I couldn't do more. And I compared the same. I took the differences that we got for each argument of latitude, and I tried to look at when these differences were as little as possible. And from this plot, in which indeed we have the mean delta wind, let's say, between the 3 subsets of zonal winds, we get that indeed we have a minimum that is between indeed 0.8 and 0.9, with an average of 0.85, that is providing indeed an idea that we are below 0.93 that is currently used. So this might be more consistent value for the next processing. So if we look exactly at the zonal wind themselves, I split the analysis in ascending orbit sectors and descending orbit sectors. Here I have in ascending orbit sector zonal wind in color bar, MLAT on the vertical axis, and time on the horizontal. This is what we got before, and this is what we get now. So I can play around with them, but the structure basically doesn't change, but it's just changing the magnitude. The winds are scaling down. Same thing for the descending orbit sector. Oops. Yeah. So unluckily for Goce, was not possible to do such a study because Goce was a pretty stable satellite. was staying in the range of very narrow ranges of side slip, so it was impossible to do a maneuver analysis. But luckily, indeed, there was sun synchronous orbit, so there were not local time changes in the studies, and we could do pretty much a seasonal analysis. So I took 3 years of data between January 2010 and January 2013, and I looked at different seasons. So being in the data 4 months for the December solstice, around indeed the December solstice equinoxes, other 4 months, and June solstice, other 4 months, and I split the analysis in the dusk down sectors. So dusk is ascending and descending is down. And what we got again is that the accommodation coefficient, the minimum one, the optimal one that looks like, is lower again with respect to 0.93, and is providing like an average of 0.82 that is currently used in the new version of Gauche data that we released, I think, more or less 1 month ago as part of the ESA documentation.
Could you say again what the physical meaning of the accommodation coefficient is?
Basically, it's giving you an idea of the energy exchange between the atmospheric particles and the surfaces of the satellite.
Wait, if it's one, what's the...
One basically is when it's fully diffusive. So the particle is reflecting in a fully diffusive way.
Right.
And indeed, it means that the particle temperature is adjusting to the wall temperature of the satellite.
And as it gets lower, that means the reflection is more specular?
Let's say that if the temperature is not adjusting, is still higher, and obviously there is a middle way. Let's say it's not only specular. There are quasi-specular reflections or quasi-diffusive reflections, and it's ranging between these two possibilities.
Well, let me ask it a different way. If you had a purely specular reflection, what would alpha E be?
Specular reflection, 0.
Okay.
Because the temperature is not changing. Is equal to the So yeah, the reflected temperature is equal to the incoming temperature.
So 0
just
is specular, 1 is diffusive, and everything in between is a complex mixture. I got it.
Exactly. And if you are close to the diffusive reflection mode, you can mainly describe it again indeed with the energy accumulation coefficient. Yeah. So indeed, this is a bit of advertisement as well. I know that a lot of you are working with Gauche level 2, Gauche densities and winds, and what we did indeed is to release, I think indeed 1 month ago, the new version of Gauche data that are using the 0.82 coefficient that we found out, and indeed you can find it at this link that you see below. You just click here, easy peasy, you don't need to register, it's very fast. You get your time series easily. Another thing is it's not easy to work with gas surface interactions with the densities, but what we could do, and is what I'm trying to do in these last months, is to look at swarm mission and exactly at swarm alpha and swarm Charlie data. As you can see from the altitude point of view, here again is an altitude plot, is a function of time. Swarm A and C are pretty much flying at the same altitude, and also if we look at the maneuver that happened in 2014, May 2014, we can see that also the differences in latitude. I selected 3 different periods close to the maneuver. Mainly we are looking at the full circles are for swarm A, the empty circles are for swarm C. We are looking at nearly the same atmosphere and thermosphere. So what we can do is if we look at, as we did for the wind, like the density of the previous day or the day after, results are going to be not so consistent because the density is really sensitive to the variation in the solar activity. But what we can do is to look at the same time at the two satellite data that are approaching the wind in a different aerodynamic, in a different, let's say, geometry. Let's say. So, indeed, in this maneuver, basically, on the left side of this animation, we see the yaw angle variation. In orange, I think, is for swarm C, and for the gray is for swarm A, and in a few seconds you might see swarm A changing the direction. The blue vector on the left are for the velocity, the incoming velocity. The yellow arrow is for the POD acceleration, so from the GPS. The orange colors are for the accelerations modeled with the accommodation coefficient that is going from the brightest color, it's 1, and is decreasing to 0.4 in the darker. And if you have very good eyes, you might spot also the solar radiation acceleration. In the middle is a red arrow close to the center of mass of the satellite. Obviously, the aerodynamic accelerations were much stronger because we were in high solar activity, so more dense atmosphere with respect to the solar radiation. And on the right, we try to see at the densities from the two satellites for different accommodation coefficient. The white is for an analysis, the blue for the X and Y, depending on what's the attitude of the satellite. And what we could try to do is to look at the different accommodation coefficients and see where, for which accommodation coefficient, these differences between these two satellites are minimal. So what I did is indeed to look again. Here we have again the yaw angle on the top. Dashed lines are for swarm C, continuous lines are for swarm A. I try to pick up all the possible orbit periods, and in the second plot below, we see the density ratio between the two satellites as a function of the accommodation coefficient. And also here is kind of providing us an idea that the accommodation coefficient, the optimal one, might be lower than 0.93 and maybe indeed between 0.8 and 0.9, and this might be included in the next dissemination of the data soon. So this is indeed a future work. I mean, I'm working on it right now for what concerns the swarm maneuver analysis. But if I will select some future works that we need to improve still, is improving the solar radiation pressure modeling. This is really important, for example, now that we are approaching solar minimum. I mean, we are fully in solar minimum, because as we can see here from swarm A x-axis acceleration, we get that the blue are accelerations due to the aerodynamic forces, and the yellow ones are for the radiation pressure. So you see here on the recent data that these are getting pretty close to each other. So if you have some problems in modeling the solar radiation pressure, your output, your product of the density will be highly affected by that. This is even more visible if we look at swarm B data, because it's flying higher, and indeed we are nearly at the same contribution between aerodynamics and solar radiation pressure acceleration. So this is something that we would like to do. Let's see if we will have time. And indeed, what I did 1 year and a half, I don't remember, is to work on a new software able to look at what is in view of the sun. So basically is creating an output of accelerations depending on the orientation of the sun with respect to the satellite, and see what is in view, what is what is not, and is creating indeed an output of accelerations that we can subtract from the accelerometer data. Another future work that is less future, because it's something that we might do indeed, we will do here at HAO together with Federico Gasperini. We will try to look at Champ and Grace. We will start for Champ and Grace data and try to see how these new densities are affecting the current physics-based models like WACAMAX, for example. So what we will try in the first part of my period here is to use SATIST, and today Federico told me that we succeeded to let it work, and we will try to indeed give the input from CHAMP and GRACE, and have the densities from this in this way. And what we could do after, what we're trying to do is to look at the simulation of the data from CHAMP and GRACE. We could do what we could do is to assimilate before CHAMP and create a new version of a WACAMAX, and also do the same for GRACE, and maybe after create another one that is assimilating the two, and intercompare the results and see if what we get. I personally not an expert of data simulation, so if in the audience there is someone interested in, we will be super happy to chat about it. So this concludes my presentation. I will be here at HAO for these 2 months, in June and July, and I'm going to be there on the second floor, so if you want to talk about something and you have some new ideas, I will be happy to talk with you. That's it.
Thank you for the talk. Questions? Yeah?
When you're going from the Gunther altitudes up to the GRACE altitudes, the actual composition of the atmosphere is a bit different. You've got more sort of N2 down at 250, and then maybe more helium compared with the oxygen at the higher altitudes. For your energy accommodation coefficient, do you not have to take into account the fact that whether it's that mixture of species, or is that such a second order effect that you don't have to worry about?
Yeah, I'm mostly looking at the satellite data themselves, so I'm not modeling the chemistry close to the surface of the satellite. I'm aware that a lot of people worked on that. Basically, what I assume as input for the chemistry is coming from semi-empirical models. This is something that indeed, or we approach the problem as like some people is doing with the Langmuir isotherms or different ways. But indeed, our input from the chemistry is mostly driven by the semi-empirical models.
So all of that gets wrapped up in your alpha E term, presumably. Is that right? That coefficient will, whatever the interaction is, will.
Let's say that
dependence on the mixture of the species will have all been wrapped up in how you had to adjust that.
Yeah.
That accommodation coefficient of the.
Mainly what I do is a kind of reverse engineering approach. So I look at the data, and from those ones, I try to find an optimal value of the accommodation coefficient. But I don't say like there is 80% of helium or whatever, and the accommodation coefficient for me is not a function of the chemistry directly, let's say. It's indirectly.
So it's wrapped up. So that leads to the question of, do you find a different energy accommodation coefficient at GRACE and Gunther that might reflect that?
I could say that indeed, from what I'm seeing, Gunther has a slightly lower accommodation coefficient of 0.82 with respect, for example, what we are seeing for CHAMP. From CHAMP, I'm pretty sure about that. I have quite consistent results. Swarm, I'm working on it, and also there looks like it's around 0.85 again. GRACE is a little bit more difficult to deal with because for the winds we are a little bit high in altitude, so it's a bit indeed more difficult to deal with. But indeed for Gunther, again, what we are finding is that we have an average accommodation coefficient that is slightly lower. Yeah, mostly, yeah, this is...
Sort of along the same line. So are you using constant of
alpha E parameter for all the data set, all the years, because with time going, the satellite altitude actually slowly decreasing, right? So you would imagine that all the particles composition, all these changes, so alpha parameter will be changed as well.
So you will mean like if alpha E will change like the solar activity so far?
Or during the duration of the satellite
there are some papers that indeed are saying that this parameter will change with the solar activity. Nowadays, let's say we are finding this, we are trying to process all the products with one average accommodation coefficient that we are finding as optimal.
Like for the neutral wind part, you change a little, different version can be factor of 2 difference in magnitude. So I can imagine that, because my understanding is neutral wind and the density, they are sort of related. You change one, you change the other. So how much that factor of 2 difference in neutral wind magnitude change translating into the density derivation?
Well, let's say that if from this analysis, if we analyze the winds and we get an accommodation coefficient, mostly for example, working with the densities is not that easy because so we are relying on the accommodation coefficient that we get in the optimal accommodation coefficient for the different studies that we do. So if we find the 0.85 for the manoeuvre, we are sticking into that. And we might find other ways to deal with the problem, but at the moment there are, it's not really easy.
Number for the entire mission data?
At the moment, yes.
So before you had this capability, I think the data from different satellites were always normalized to some common data set like HASDM or something like that. Now you don't really need to do that because you've got a more accurate estimate of the drag coefficient. Do you find that the scale factors that you're now finding are consistent with those correction factors that people were using beforehand? Or?
Yeah. I approached also this way. Obviously, it's a bit tricky to show because anyway, what I did is to create like that kind of a bar plot, a block plot that we saw at the beginning, where there were the yellow and blue boxes. And I kind of see indeed that there is a constant, nearly constant trend of the ratio if we select an accommodation coefficient that is around 0.8, 0.85.
Okay.
But it's also not, it's mostly a qualitative approach that I don't like so much anyway, because anyway, the uncertainties in the semi-empirical models are really wide. So you get anyway an uncertainty around those points, and you cannot really find an optimal accommodation coefficient from that kind of study, because anyway, the difference, for example, from 0.93 and 0.85 might be like 10%, but the atmospheric semi-empirical model as well as like a 10-20% of uncertainty, so you are still quite wide on that margin. And yeah, you kind of see it, but is not easy to do a quantitative analysis.
Okay. Yeah, we'll talk afterwards.
Yeah.
Any more questions?
It strikes me that these satellites that have prime missions for gravitation and magnetism and so forth, geomagnetism, are designed to be somewhat aerodynamic and to minimize drag, and yet have a sensitivity of attitude to the amount of drag and lift, which serves your purposes for deriving the combination code for deriving the surface gas interactions, but it's not optimal for neutral densities or winds for that matter. What you would like for those is like nice spheres or something that are very insensitive to any attitude anomalies, and of course from the gravitational point of view, well, that's what the accelerometer is for, is to be able to take out all of that clutter, all of that noise that we find so interesting. I mean, I'm glad that we have the access to all of this drag data from an ancillary source. But it's sort of like the GPS. You know, we're always mucking about in the residue of somebody else's quality data set. And so I just wish we had a satellite of our own to do this thing the right way and other things.
Yeah. If I would have a lot of money, I would push for a mission that would be able to provide me additional information together with accelerometer, like temperature, composition. That will be ideal, because right now we are kind of, it's not easy to deal with these things. So you have to always assume something, like surface temperature, you fix it to that. If you would have something able to measure these things, we could really do very nice science. We can still, but will be very good in that case.
More questions? If not, let's thank the speaker again.